Swayam Prabha. Digital India. Educated India.
Okay, so let us continue with this, introduction and overview of differential geometry. So I was trying to tell you last time about the interesting results connected with surfaces. Okay, so I told you that the first interesting result is the so-called Gauss theorem egregium, which is Gauss's remarkable theorem, which when you state it, it doesn't look so remarkable that no portion of the surface of the earth looks like a portion of the plane, and that looks so obvious or simple for the simple reason that the curvature, the sphere is curved, sphere has a positive curvature, whereas the plane has no curvature. But then the point is, again, the math is about trying to make all these qualitative statements, completely quantify them, and write down the theory for that, and that's where it becomes non-trivial and remarkable. Okay, that's something that we will prove in this course. Okay, and then the other important theorem I was talking about was the Gauss-Bonnet theorem. Okay, and the Gauss-Bonnet theorem is a class of it's a class of several types of theorems, and these are valid in several dimensions. I was trying to tell you about the Gauss-Bonnet for surfaces, and I was only trying to tell you two cases. So I gave you the case of I gave you the case of a sphere. I told you that if you give me a surface, you can write down, or you can make what is called a triangulation. Okay, that means you break the surface into triangles. Now, if the surface is a region in the plane, or if it is a plane, part of a plane, then you can actually use actual triangles. Okay, but then if the surface is curved, then you are allowed to use curvilinear triangles, which means these are triangles with the three sides being curves. Okay, and then what is the triangulation? The rule of triangulation is that any two such triangles can only meet at a point, and if they meet at 2 points, then they should have the common edge. The common edge should belong to both of them. Okay, and the big deal is that for any triangulation, you have what is called the Euler characteristic, which is the expression V minus E plus F. V is the number of vertices, where you have to count all the vertices of the triangles, and then E is the number of edges. Okay, it doesn't matter whether the edges are straight or curved. Okay, and F is the number of faces, which is essentially the number of triangles. Okay, you calculate this V minus E plus F, and then what you get is called the Euler characteristic chi of the surface. And the interesting thing is that this Euler characteristic is a topological invariant. It will not change if you continuously deform the surface. Okay, so for example, a cube, or for that matter a cuboid, or you can take a parallelepiped, or you take a tetrahedron or dodecahedron or icosahedron or sphere, they are all deformable from one to the other, and they all have Euler characteristic of 2. Okay, and similarly, if you try to do it to a surface, to another type of surface, which is a torus, then you get a Euler characteristic of 0. Okay, and therefore this Euler characteristic has got nothing to do with smoothness. Okay, on the other hand, curvature has got to do with smoothness. Okay, curvature, as you know, is largely the second derivative term, so it does involve smoothness. Okay, at least second continuous differentiability is involved. And the Gauss-Bonnet theorem says something amazing. It says that you calculate the total curvature, okay, and that is 2 pi times the Euler characteristic. And the interesting thing is the thing on the left for smooth objects is defined only for smooth objects, whereas the Euler characteristic is defined for even sharp objects. Okay, and I was trying to explain what is of course, by itself it is an interesting thing, because the quantity on the left, you see, is depends on calculus. The curvature depends on calculus. The quantity on the right is Euler characteristic. It depends only on the topology. It doesn't have anything to do with smoothness. That these two are related is already an amazing thing. And for example, I was trying to explain how would you appreciate this? So I said that, for example, if you take a sphere, okay, the Euler characteristic is 2, and the total curvature will be 2 pi into 2, so it will be 4 pi. All right. Now you see, now you take that sphere and then you slightly deform it smoothly. Okay, don't pinch it or make any corners. You think of it as a slightly deflated football. Okay, then what happens is that you get something like this. Okay, and the point is that even for this it holds. The total curvature is still 2. I mean is still 4 pi, 2 pi into 2, 4 pi. So the total curvature here and the total curvature here there are the same. Okay, of course you can explain this away by saying that in portions where it's folding in, where it's having a it's curving inwards, it's compensated by the other places where it's going to get bulged outwards or something like that. But then these are all very qualitative things. To say exactly that you get the same value, that's not an obvious thing. Okay, but that's what the Gauss-Bonnet says. So this rather deflated or slightly smoothly deformed football or sphere and the original sphere, they both have the same Euler characteristic, and therefore they have the same total curvature. That's not obvious. Okay, and it really doesn't. It's interesting that you mold it, you do this deformation in any way, except that make sure it is smooth, so that curvature is defined at every point in a nice way, continuously. Then it's not going to change, and that's not obvious. Okay, so the one way of deducing it is because it is equal to the topological Euler characteristic is involved. Okay, that multiplied by 2 pi, and that topological Euler characteristic does not change, because if I make a triangulation of the sphere, okay, then the triangulation will still live on the surface of the the deformed, smoothly deformed sphere, and it will still give me the number of vertices, the number of edges, the number of faces is not going to change. So you see, the Euler characteristic is not going to change. Okay, but then the theorem says that therefore the curvature will not change, the total curvature. Okay, and of course I told you what I mean here is curvature. Total curvature means you have to take curvature at every point and then sum it up over the whole surface of the sphere, so it's going to be a surface integral. Okay, that's how it's going to be made sense of. Okay, but I'll come more towards that in today's lecture. And again, in the case of the torus, I told you the Euler characteristic is 0. Okay, and so if you slightly deform the torus, here also the Euler characteristic will be 0. Okay, that means the total curvature is 0. Okay, and so you see, so this is a remarkable thing. Now what I want to say is, I want to get into this aspect of how do you measure curvature of a surface. Okay, so that's the question I want to talk about. How do you measure the curvature of a surface? So so you can imagine that there is a surface like this, a portion of the surface, and I'm trying to suppose I take a point P on the surface, and I want to measure the curvature of the surface there. So how do you do it? So the trick is that you're assuming that you can make sense of what the curvature of a curve means. Okay, then you can start trying to measure the curvatures of curves passing through that point on that surface. Okay, so that's a very natural thought. Okay, and you can make it mathematically precise. So what you can do is, you see, I want the curvature at this point P of the surface. Okay, S is the surface, P is the point on the surface. All right, and I want the curvature there. I want to make sense of curvature. So here is some interesting things are going on. The idea is very simple. The idea is try to pass a curve through P and look at its curvature. Okay, so let's do that. So what you do is that you pass a curve through this. So I'll pass a curve like this. So I call it as gamma. Gamma is a curve on S through the point P. Okay, you pass a curve through. Okay, and once you have this curve, this curve will have a curvature. All right. Now, mind you, this is not a plane curve, not necessarily a plane curve. It's a curve in space. So it's a space curve, and I have told you what happens for a space. See, for a plane curve, how do you get the curvature at a point? At a point you find the best fitting circle, which is a circle of curvature, which has the same tangent as the curve at that point, and there is a specific circle. Of course all this has to be proved, and then this specific circle has a specific radius and a center. The center is called the center of curvature at that point, and the radius is called the radius of curvature, and taking the reciprocal of the radius of curvature gives you the curvature at that point. And I told you that this is the story for plane curves, but for space curves it's more complicated. What happens in the case of space curves is that there is in fact not only to determine this circle of curvature, you need first a plane which is tangent to the curve at that point. Okay, in the sense that the tangent to the curve at that point is also a tangent direction on that plane. I mean, it's one of the directions of the plane. Okay, and you need a special plane determined at that point and a circle on that. And I told you that again this has to be proved. That plane is called the osculating plane. Okay, and this osculating plane has a circle of curvature. And then again you take the radius of the circle and you get the radius of curvature. So what happens is that in the case of a space curve, it's kind of complicated. So if I draw it like this, you see I have the tangent here at that point, tangent, and then there is a plane. So let me draw it like this. There is some plane. There is this plane which is the osculating plane for the curve at the point P. Okay, and in this osculating plane what happens is that you get a circle. So let me draw it like this. So I get a circle of curvature. And the picture is complicated in the sense that had it been a plane curve, as you move the point on the curve, you see these circles will keep changing. And but if it is a point on a space curve, not only these circles keep changing, even the osculating planes also keep fluctuating. They also keep moving because the plane keeps moving around. Okay, so at every point here the plane changes. And on the plane there is a circle that its radius also changes. Okay, that's what is happening for a space curve. All right, so there is this oscillating plane, there is a circle of curvature, and of course there will be a center of curvature. Now you see what you can do is, therefore, if you look at the now you see you are now in 3 dimensions. Okay, and you can take, for example, to measure the curvature. You need to keep, it's not enough to numerically keep track of the curvature, you need to also keep track of the direction. So I have to take the point and I have to take the center of curvature, okay, and then I have to look at that direction. That is the kind of direction of curvature. Okay, so basically if this is so let me change this diagram a bit. I will put the point here. The point is here, and then there is this center of curvature at this point, and then I have this so if I call this as the curvature vector, let's say. Okay, now so you have a curvature vector, all right, and I've already told you that the normal to the plane keeps changing, and trying to measure the rate of change of this normal to the plane is the same as measuring the change of this plane, and this is what is called as torsion. Okay, so if the torsion is 0, it means that it's a plane curve, and conversely. You have a question?
Is the tangent vector on the plane of the surface?
Absolutely. So what is happening here is that you see you have this plane. This plane contains this tangent vector. Okay, and the circle is on that plane, all right, and just to make matters less or more confusing, depends on how you think about it, there is actually another plane to the surface at that point, which is the actual tangent plane. So what happens is that now I have one more plane here like this. This is the tangent plane to the surface at the point. Alright. Now that plane, what you must understand is that that plane and this oscillating plane, they both have the tangent to the curve as a common line, lying in the common line. Okay. So this red plane that I have drawn is tangent to the surface at that point. Okay. The surface is smooth, and smoothness of a surface actually means that at every point you have a well-defined tangent plane. All right. Just like smoothness of a curve means that at every point you have a well-defined tangent line, right? So this is a smooth surface. Okay. So there is this red plane there is actually the tangent plane to the surface through the point, and this tangent vector. So this t, if you want, let me write this as t gamma p, just to signify that this is a tangent to the curve gamma at the point p, and this t gamma p is going to lie both on this this red plane, which is the tangent plane to the surface of the point, as well as this purple plane that I have added, which I have drawn, which is actually the oscillating plane. Okay. Now you see this. What I want you to understand is that these two planes are different. Okay. Now this unfortunately this is not a three-dimensional diagram, so you have to do a little bit of imagination. You see this curvature vector is now you see is pointing somewhere in space. Basically, you see, if you think of it like this, you see, if the surface is like this, let's say, and I have a point here and I have a curve going like this, then more or less you should expect some the circle of curvature somewhere below, and the curvature vector will point like this. Okay. All right. And then this curvature, now what happens is this, but you tend to study everything with respect to the surface. That means you have to study everything with respect to the tangent plane and the normal to the surface. So what you do is this curvature vector, okay, you break it into two pieces. You resolve it into two pieces. The two pieces being one along the tangent plane direction, the other along the normal to the tangent plane direction. So what happens is that this the curvature vector is broken into two components. There is one component along normal to the surface at the point, okay, which is going to be this. This is the normal to the surface at that point, and this is actually the normal to that red rectangular plane I have drawn the surface at that point. Okay, and then there is one component along that, and there is another component along the tangent plane, plus another. So let me write it here, plus another along the tangent plane to the surface at that point. Okay. See, remember the tangent plane is a two-dimensional plane. The normal plane is a one-dimensional. The normal is a one-dimensional line. So this is totally three dimensions. And any vector in three dimensions, can be resolved into in three mutually perpendicular directions, or for that matter, three mutually linearly independent, three linearly independent directions. So I can break it into a normal component. Any vector can be broken into a component which is normal to the tangent plane, and also the other component will be therefore along the tangent plane. So what happens is that this component along the normal, okay, this is given a name. This is what is called the normal curvature, K normal. This is called the K normal of gamma at the point P, and it's called the normal curvature. Okay, and this other vector, which is going along the tangent to the curve. Okay, so when you are moving on the surface, there is a terminology in differential geometry. The terminology is geodesic. Okay, so geodesic means you're keeping to the ground. Okay, in fact it means more, but I'll come to that later. You are keeping to the surface. Okay. So the tangent plane gives the direction of the surface up to first order at any point. So the component along the tangent plane is what is called the geodesic curvature. So you see the curvature vector breaks into two pieces. There is one vector, there's one component which goes along the normal to the tangent plane and to the surface at that point. That's the normal curvature. And then the other component will be along the tangent plane to the surface at that point, and that's called the geodesic curvature. So this guy is called K geodesic at P of gamma. So basically, if you want to use more slick notation, I'll write as Kn at P of gamma, and this can be written as K small g at P of gamma. So you see, basically I just want to introduce these two objects. There is a so every if you take a point on the surface and pass a curve through it, okay, the curvature vector breaks into two pieces, one along the normal direction, which is called the normal curvature, then one along the tangent direction called the geodesic curvature. And of course the sum of these two vectors will be your total curvature vector. So basically what you are doing is you are seeing, see, what are you doing by breaking like this? You are looking at what amount of curvature is normal to the surface, and what part of it is tangent to the surface. That's all. The normal curvature gives you the component of curvature that is normal to the surface, and the geodesic curvature gives you the component along the tangent to the surface. Okay. Now, how much the surface is curved should be controlled by what? It should be controlled only by the normal curvature. Okay. See, along the surface, you can move in so many ways. That's not going to tell you anything about how curved the surface is. Okay. For example, on the plane also I can keep moving. If you play this game on the plane, what happens is that the oscillating plane is the plane itself for any plane curve, and the tangent plane to at any point is also the plane. Okay. And you see the curvature vector is on the plane. All right. And what happens therefore is that you will only, the normal curvature component will be 0, and you see you will get only a component along the plane itself, which is the geodesic curvature. So for plane curves you have normal curvature 0, and that also, and that correlated with the fact that the plane is 0 curvature. Okay. So the moral of the story is, you see, it's the normal curvature that should kind of decently measure the curvature, not the geodesic curvature. So here is the recipe. The recipe is, so this is all due to Gauss, okay, several hundred years ago. So this is all due to Gauss. So what you do is that now you start, take a point on the surface, keep drawing curves, and for every curve at that point you calculate the normal curvature. That means through various curves passing through that point, you start calculating the normal curvature, which is kind of supposed to measure how much the surface is curving at that point. Okay. So that is the recipe. Okay. So let me write this down. We calculate K normal curvature at the point P for gamma for all possible gamma through P on the surface. Okay. So the picture is more like this. I have this point P, and then I draw a curve like this, the gamma 1, then I draw another curve like this is gamma 2, I draw another curve like this is gamma 3. Okay. And each of these curves is going to give me a normal curvature. So corresponding to gamma 1, I am going to get K normal gamma 1 at P, and then similarly for gamma 2 and gamma 3. Okay. And somehow if you have all these data together, that should kind of tell you how much the surface is curved at that point. Okay. So up to this, it's kind of very qualitative and it's kind of very understandable. So here's where something amazing happens. Okay. Now these normal curvatures, okay, of various curves as you pass various curves to the point, they have a minimum and a maximum. Okay. So there is a maximum normal curvature and there is a minimal normal curvature that is attained. Okay. So that's the first thing. All right. And you can more or less believe this if you believe that the normal curvature is a kind of continuous function of the curve, and this curve is on a connected surface, and then by some kind of intermediate value philosophy, you can expect that the values that are being taken in a closed bounded interval, and the left end point will be the minimum and the right end point will be the maximum. Okay. So therefore the moral of the story is that it's believable that there is a minimum normal curvature and there is a maximal normal curvature. Okay. But again, this is to be mathematically proved. What is more interesting is that these two, so there is a curve which gives a minimal normal curvature, there is a curve which gives a maximal normal curvature. The amazing thing is that this happens in perpendicular directions. Okay, so this is something that is not directly obvious. Okay, and in fact what happens is that what works here is some linear algebra, okay, along with some calculus, and if you want to seriously see it, it's also differential equations and evolution of differential equations. Okay, so what is happening geometrically is that there are two perpendicular directions, okay, along which these normal curvature, maximal and minimal normal curvatures are attained. Okay, so that this is one of the most important results. So let me say this: what happens is the following. On the surface at this point P, you have two directions. You have this two, and mind you, this is all on the surface, so they are tangent directions. So you have T1. So I will call this as, so there is a, so let me put it as, there is a curve gamma minimum, okay, through the point P, and I'll call it gamma minimum, and the corresponding to this curve you get the normal curvature Kn is minimum, okay, and this value is Kn at P is minimum. So this Kn minimum, so I will simply call it as K min at P, okay, and then there is another direction. So this is in the direction, so this is T gamma minimum is this direction. Then there is another direction which is exactly at 90 degrees, okay, and there is another curve like this, okay, and what is happening along this direction is T gamma maximum, okay, and so let me write that gamma correctly, okay, and this is your curve gamma maximum, okay, and the big deal is that these two are 90 degrees to each other, and corresponding to this gamma maximum, you are getting a normal, the K normal, the normal curvature at the point P is a maximum. Okay, so this is something that happens, and this has to be proved. This uses linear algebra, okay, and some geometry, and some, of course, some calculus. Okay, mind you, curvature is already second derivative. Okay, and mind you, a surface is now going to have two independent variables. So you are going to involve partial derivatives of functions of two variables. Okay, so essentially it will be like studying the so-called Hessian that you studied for a surface while trying to understand maxima minima for multivariable calculus. Okay, and you study maxima minima saddle point conditions. It's essentially that kind of study. Okay, so this is something that has to be proved, but it's amazing that it happens in two perpendicular directions. All right, always. Mind you, there is a possibility that this maximum and minimum is always equal. For example, if you take a sphere, at every point you draw a circle, then if you draw a big circle, for example, if you draw all big circles through a point on the sphere, you will see that the curvature vector is going to be the vector that points to the center of the sphere, and is going to be constant. So therefore the normal curvature is going to be the same. Okay, the sphere is curved in the same way in all directions if you want. All right, so this maximum minimum, when I say, mind you, they can be equal, which means that the curvature is constant. Okay, so anyway, now what did Gauss do? So what Gauss did is he introduced two, since you have two curvatures now on a surface, now how do you, so our aim is to understand what curvature on surface is, but we are getting two pieces of data. You're getting a minimum and you're getting a maximum, all right? And by the way, these are called principal curvatures, okay, at that point. Now how do you deal with these two guys? So what Gauss did, he was smart enough to do two things. I mean, if you want to to easily understand two quantities, one easy way is take the average, okay, and which is the mean, okay, and you can take two types of means. You can take arithmetic mean and you can take geometric mean. All right. So what is the arithmetic mean? You can take the average of these two, okay, and when you take arithmetic mean of these two, you get what is called the mean curvature, okay, and then you can take geometric mean of these two. But geometric mean will mean that you have to take product and then take square root, but I don't want to have the square root all the time coming in. So studying the square root is the same as studying quantity without the square root, because they are proportional. I mean they can be kept track of without having to worry about the square root at all times. So what Gauss did was he took product of these two curvatures, okay, and this product of these two curvatures is what is called the Gaussian curvature. Okay, so you have K Gaussian at the point P is actually the product K minimum at P times K maximum at P, and then K mean curvature at P. Some of the books use H, and this is going to be the average. So K mean at P plus K max at P divided by 2. Okay. So you have the Gaussian curvature and the mean curvature, and then Gauss was able to show with the theory that if you want to understand the curvature of a surface completely at every point, it's enough to just study these two. It's enough to just know the mean and Gaussian curvatures. Then you know the full knowledge. You have full knowledge about the curvature on the surface. In fact, you have complete knowledge about the curvature of any curve on the surface through any point. You can compute it using this. These are remarkable numbers. Okay. So the whole curvature theory of surfaces is controlled by these two. All right. So this is the so-called Gaussian curvature and mean curvature. Mind you, the mean curvature is actually a mean. The Gaussian curvature is not a geometric mean; it's square of the geometric mean. Okay. So now, this is to tell you how this curvature is being measured on a surface. Okay. And now you see, I can now tell you what do you mean by total curvature of a surface. You take this Gaussian curvature at every point, that's a function at every point. It's a scalar function at every point. At every point I am giving you a magnitude, alright. Of course it's signed, okay. So mind you, these are all defined using the normal curvatures, and the normal curvatures has a normal direction, but then there is always a sign to tell you whether something is curving upward or outward or inward. Okay, so it's a signed real number. So it's basically it's not a non-negative real number, but it's a real number. Okay, and for example, if you take something like a saddle, there's a minimum like this. Okay, then what happens is in this direction, the circle of curvature will be here. It will be pointing like this. And in this direction, the circle of curvature will be in the opposite direction, it will be pointing like this. So if you take the product, you will get a negative value. So at a saddle, you see, you get negative Gaussian curvature. Okay. Whereas if you take something curved like a bowl or a sphere, on one side if you keep a sign convention, if you look at it in one side as positive and the other side is negative, either you will get a product of two positives or you will get a product of two negatives if you look at it the other side. In any case, you will get only positive curvature. Okay. So you see, you have immediately this introduces surfaces of positive and negative curvature. What is happening in a torus is that the outer bulged portion of the torus is positive curvature. The inner portion of the torus, okay, which is like this, that is negative curvature. Because what is happening is that one curve is like this, the other one is in the other direction. It's at every point it's a saddle if you think about it, the inner portion of a torus. Okay, and of course the Euler characteristic is 0. So by Gauss-Bonnet, what is happening is the total negative curvature given by the inner part is cancelling out to the total positive curvature given by the outer part. But now what is the curvature? The curvature is the Gaussian curvature. Okay, that's how you get these signs. Okay, so now you see what I wanted to say is um, uh, yeah. So what do you mean by total curvature? It's so you see this, the Gaussian curvature is a non-negative. I mean it is a not non-negative. It is a function, real valued function, and it can take positive or negative values. Okay. What you do, but because everything is smooth, you see we always put this condition that everything that is involved, the second derivatives are all continuous. Okay. Then you can show that this Gaussian curvature function is also continuous. Okay. And this function varies over points on the surface. What you can do is now you can take the surface integral over the surface of this function, and that is the total curvature, and that's the total curvature term that comes in the Gauss-Bonnet theorem. Okay. So the moral of the story is that's how you make sense of the total curvature. So when I say total curvature of a curved surface, I mean total Gaussian curvature. Okay. So if you take what is the easiest example? You take a sphere of radius 1. Okay. Then you take any point. At any point, you see that you will get if you draw any great circle on that. Okay. You see you will get maximum curvature only for the great circles. Okay. Not for circles that go out like this. Okay. To draw curves on the sphere, you could as well draw circles. You can convince yourself that you will get the maximum curvature only if you draw, maximum normal curvature only if you draw something for which the normal curvature vector is normal to the surface. That naturally happens for all the great circles, the circles which have the same center as the center of the sphere. And then what happens is that if you, all these circles have radius 1. Therefore, the radius of curvature is 1. Therefore, curvature is 1. Therefore, if you take two orthogonal directions, the product of curvatures is 1. Okay. And what is the total curvature? What is the total curvature? I have to integrate this Gaussian curvature function is 1. It's a constant function 1. I have to integrate it over the surface of the sphere. Okay. But if you integrate a constant function, it is just, you can take the constant out. The integral is just the total surface area. What is the total surface area of a sphere? It's 4 pi r squared. If r is 1, it's 4 pi. So what is the total Gaussian curvature? It is 4 pi. What does the Gauss-Bonnet theorem say? It is 2 pi chi. What is chi? Chi is 2. So that's also 4 pi. So you see this verifies Gauss-Bonnet theorem for the sphere. You can see it directly. Okay. What is not obvious is that if I slightly, deform that sphere, and now, the Gaussian curvature function is going to change. You still add it up, it's still going to give you 4 pi. That's not obvious. Okay. That's what you have to appreciate. Okay. So you see, you can see the Gauss-Bonnet theorem in this case, right? So, so let me say total curvature. So Gaussian curvature function k g is equal to 1. Total curvature is integral over surface integral over area of so region or spheres surface of kg, and this is going to be integral over the sphere surface. So, and I have to put d. So when you write the integral, of course I have to write dA. Okay, you can use dA, or because it's a curved surface, if you want to use d sigma, where d sigma is the element of curved surface area. Then this will be equal to integral over the sphere surface d sigma, and this is just going to give you 4 pi. And notice that this is also equal to 4 pi, this is also equal to 2 pi chi, and that's Gauss-Bonnet. Okay. Right. So okay, so now you can literally see Gauss-Bonnet here. Now what I'm going to do is of course you can answer many questions, such as if there is a surface which has constant Gaussian curvature, same constant value, then it must be a sphere. You should expect this, right? Now you can prove such statements. Okay, such geometric statements that seem intuitive. If a surface is, it's a closed surface, bounded surface, and it's curved in the same way in all directions at every point, it has to be a sphere. Right? If you have a plane curve such that the curvature is constant at every point, then either it should be a straight line or it should be a circle. Should happen, right? Similarly, if you have a curve, a space curve for which the curvature and torsion are constant as scalars, okay, then what do you expect it to be? You will get a helix. Okay, the helix, you see, the rate at which it is moving out of its oscillating plane is kind of constant. Okay. Okay. So all these statements can be now mathematically proved with differential geometry. Okay. So that is about this. Now I am going to come to another part of the story, which has got to do with the idea of geodesics. Okay. So I am going to come to this thing called geodesics. So geodesics. Oops. So what is this idea of geodesics? See, the idea of geodesic is basically you are trying to find a path of shortest distance. Okay, to find paths of shortest distance. So this is the idea is very simple. At least on the plane, the shortest distance between 2 points is a straight line. Okay, and of course, if you take for that matter in Euclidean space in any dimensions, the shortest distance between any 2 points is a straight line segment distance. Okay, but it's only when you are worried about curved things that things start becoming different. So imagine a surface and you have 2 points on the surface, and I want to find a path of shortest length. Okay, now these kind of paths are what are called as geodesics. Now there is a way of finding this and quantifying this, writing down formulas and theorems and properties. This is done in differential geometry, and this is very, very important. For example, if you take something as complicated as, let's say, the Mars lander is on the surface of Mars, and then there is a kind of wavy terrain. Okay, and of course you don't expect it to be smooth, but you can make a smooth approximation of that. And then you needed, suppose you have to this robot or whatever it is, this vehicle has to go from one point to another point. Okay, then I need to know which is the best possible route, which is the shortest possible distance, and that's probably because I need to save on fuel. Okay, for example. Okay, so the moral of the story is that even for navigation, even for doing these kinds of, suppose you are on in a mountainous region, and you are in one portion of the mountain and you have to reach some other place, and in the middle it's a kind of wavy mountainous terrain, and you want a path which is, let's say, the shortest path, then you should be able to find that. You should be able to find that curve on the surface. Okay, so this is about geodesics on a surface. So the idea of geodesics is to find in a region of space which is curved, okay, find the distance between 2 points, right? And so how are they relevant? Of course, they are. You can see practically they are relevant for various reasons. Okay, so let me write this: finding, paths of shortest distance between 2 points of a surface. More generally, it can be between 2 points of a region in space. Okay, so in fact, suppose I want to travel to some distant galaxy. I mean, this is a lot of imagination, and then I can think of the straight line, from my place to that. Okay, but yet that may not be the geodesic. The reason is, for example, general relativity will tell you that space is curved because there is acceleration due to gravity, which is introducing a curvature. So your space is not this good old Euclidean space, space is curved. Therefore, in that your straight line path is not a straight line, it will be a curve. Okay. For example, that's it's only because of the distortion of gravity that light from distant stars are bent by massive objects, as has been observed. Okay. So what is happening is that the acceleration due to gravity is basically its acceleration, so it's curvature. So you see the curvature has changed. The straight line is no longer the shortest path. Okay. So that's what is happening. So so it's very, very relevant. Okay. And at least we are going to look at only 3 cases to begin with. What are the 3 cases? They are the 3 fundamental cases of 3 types of geometries. There's one which is called flat geometry, which is the geometry on the plane. And there what happens is that the geodesics are just straight line segments. They're the plain old plane geometry, the usual Euclidean geometry that we do. Okay. So that is the case of, and what is this case? Is the case of zero curvature. Okay. Then there is a geometry on the sphere, which is very relevant because we live on the surface of the sphere, the Earth. And on the surface of the sphere, again you can talk about geodesics. And what happens to the geodesics? These become arcs of great circles. So, so let me write this. So, so you have this. Let me put it like this. This is plane geometry. Okay. Then there is then you have geometry on the surface of a sphere. This is called spherical geometry. And then you have something else which is called as hyperbolic geometry. Okay. And you can imagine that this is trying to understand a negatively curved geometry. So here the curvature is 0, here the curvature is positive, and here the curvature is negative. And at least as far as, so it's always somewhat hard to imagine the negative curvature thing. If you want to think of a surface which always has negative curvature, okay. To begin with, I already told you the inner region of torus, that has negative curvature because at every point it has there is a saddle. Okay. Now there is an object which is like a trumpet. Okay. Like this. Okay. And just like this is called the sphere, this is called the pseudosphere. Okay. And it looks like a trumpet, and the point I want you to understand is that at every point there you will have negative curvature, because in one direction you will have positive curvature, and whereas in the other direction you will have negative curvature. And therefore when you take product of curvatures you will get a minus sign. Now there is a deeper theorem to say that you cannot have a closed surface of negative curvature, you cannot see it in 3 dimensions. So I have to cut it somewhere, that's why this thing is cut. Okay. Whereas in the case of the sphere, I can see the whole sphere which is compact. I can see the whole sphere with positive curvature in 3 dimensions. But something in negative curvature, a closed thing, you cannot see it in 3 dimensions. This is because of topological reasons, you cannot embed it. Okay. And theorems like this can be proved using differential geometry. Okay. You cannot embed everything. But this is a nice model, it's called the pseudosphere. Alright. And you see, what happens is that you can make the curvature constant, and you can make it 1 if you want, and that is the case of a sphere. And you can make it -1, that is the case of a pseudosphere. Right? And the picture looks roughly like this. The surface looks roughly like this. Okay? It is, as you can see, there is a curve like this in the if you want the xy plane, and I am just rotating it, and that's what gives you the pseudosphere. And it has all these nice properties, except that you cannot get a completely closed surface in 3 dimensions. Okay. Now here comes so what are the geodesics? Geodesics here in the plane geometry case, they are straight line segments. And in the case of spherical geometry, these are going to be, see, if I take 2 points on the sphere, if it is in 3D, I could have as well joined those 2 points and taken the chord, but that's not allowed. I am supposed to move only on the sphere. So if you can see that the shortest distance you will get only along the arc of the big circle, okay, which is a circle on the sphere passing through those 2 points with center the same as the center of the sphere. That is a plane section of the sphere through the center of the sphere, which contains those 2 points. And here there is usually a minor arc and a major arc, and you can take the minor arc. Okay, so these are, so let me write this, these are minor arcs of great circles. Okay, and what happens in hyperbolic geometry is something of a magical thing. Okay, so in hyperbolic geometry, you know, there is a way of, you know, looking at it by projecting it onto a piece of the plane, and which piece of the plane you can project this hyperbolic geometry to get a shadow of it on the unit disk. Okay, and then you can do the geometry, hyperbolic geometry on the unit disk. So what you can do is, here you can do this on the unit disk. So there is a what is called as a unit disk model. Okay, and this is very much connected with complex analysis. Okay, where the unit disk is the same as the upper half plane or any half plane because of Mobius transformations. Okay, so the unit disk model, so I will tell you what happens in the unit disk model. So it's very, very interesting, you should really appreciate it. You see, this is a plane, and I take this unit disk, which is the disk centered at the origin, radius 1. All right. Now, if I treat it as portion of the plane, this is a, you know, of course, a flat surface. There is no curvature. Okay. But the point is that it's possible to put a different metric on this. Okay, called the hyperbolic metric. That's a new distance function. And the funny thing about this distance function is, for that distance function, something strange is going to happen. With respect to the ordinary distance function, the distance between 2 points on the unit disk cannot exceed 2. In fact, it will be strictly less than 2, right? Whereas this hyperbolic distance, as it is called, the distance from a central point to a point on the boundary will go to infinity as the point approaches the boundary. That means that this unit disk under the hyperbolic distance is unbounded. Okay, it's like the usual whole plane which is unbounded under the usual distance metric. Okay, so there is a hyperbolic metric. Okay, the beauty is, because of complex analysis, you are able to see this negative stuff happening right in front of your eyes, you know, in a bounded region. That's because of projective geometry and complex analysis. So what happens is that you have a hyperbolic metric. The distance from 0 to p will go to infinity under the hyperbolic metric as p approaches the boundary circle. Therefore, this this is an unbounded object. Okay, you have to understand that. And what are the geodesics? So that's what I want to tell you, something very, very interesting about. Okay, suppose I take 2 points, let us say q1 and q2. Okay, if it was the ordinary plane, then, you know, this would have been the shortest distance. Okay, but what happens in hyperbolic geometry is the shortest distance is actually seemingly longer when compared to the usual, what happens in the usual plane. So what you have to do is you have to take the circle passing through these 2 points and orthogonal to the unit circle. So I have to draw a circle like this. Okay, this circle is orthogonal to the unit circle, so it is, if I draw the tangent here, it is 90 degrees, okay, and if I draw the tangent here, it is 90 degrees. And believe it or not, here is the amazing thing. You see, this distance, this red distance along this curved thing is lesser in the hyperbolic metric than the straight distance. Okay, so that's how the hyperbolic metric behaves. Okay, it's amazing to see that. This is what happens in negative curvature. You seem to be traveling more, but actually you are traveling less. Okay, so it's a kind of it's kind of, you know, inspires fantasy and you know, imagination, but it happens. It's really true. Mathematically, you can write this down. Okay, so the geodesics on this unit disk and for the hyperbolic metric, they are all going to be like this. Okay, of course, if you take 2 points on the diameter, okay, it will be the straight line segment. That's because the diameter is the circle orthogonal to the unit circle and passing through those 2 points. And you are thinking of even a straight line as a circle with infinite radius. See, if 2 points are on a diameter, okay, what am I supposed to do? I am supposed to draw a circle passing through these 2 points and which is orthogonal to the original circle. But then that has to be only this diameter, it has to have infinite radius. The circle should have infinite radius, it should be a line segment. So the diameters are all going to be, geodesics, okay. But apart from the diameters, you take any points outside, then it's going to be, curved. And the curved distance is less than the straight distance, okay. That's how the hyperbolic metric behaves. So it's kind of very curious, okay. So these are 3 aspects in which, these 3 geometries differ, okay. Now I have to come to another interesting thing, which is what happens to trigonometry, okay. And what happens to this very simple statement that the sum of 3 angles of a triangle is 180 degrees, okay. Now that, believe it or not, has a generalization which is essentially the Gauss-Bonnet theorem for curves, and it works on a surface, and it has some amazing consequences, okay, which lead to what is called as spherical trigonometry and hyperbolic trigonometry, okay. So just like you have plane trigonometry, okay, you also have spherical trigonometry. So plane trigonometry is a trigonometry for the plane geometry, flat situation, zero curvature, okay. But there's also a trigonometry that works on a sphere. There's also a trigonometry that works on a hyperboloid, okay. And these trigonometries can also be studied, and this is all very much within the ambit of differential geometry, okay. So that's the next thing I want to tell you. So I think I will stop here. We will continue in the next lecture.